Greetings. There are assumptions in engineering which we do make them at some stage, and then we never ask their validity or range of their validities and keep them always and use them. But sometimes it pays to have another look at them and ask, are they really as good as what we think or what we assumed or not? One of these assumptions, which is very popular and almost you can find it in any thermodynamics books, is on the process of throttling. In the throttling, we usually assume that inlet and outlet velocities are equal. But are they? Are they always? Now, the problem I'm going to solve for you now just tries to approach this question for a very simple problem and see what does that mean when we say that the velocities at inlet and outlet are equal, and are there cases where such assumption would be not a very good assumption, or we have to make considerations for it. Now, let's go to our whiteboard and see the very simple problem of throttling. Assume that there is a valve in a pipeline. Call this I and call this E, inlet and exit. And the common pattern for the simplifying the thermodynamic equations for this problem is that we write the equations, and I just show you the equations here. You see, simplifying these equations is very simple because since there is a steady problem, the terms on the left-hand side both vanish, and so the inlet mass would equal the exit mass. Usually we assume that there is no heat transfer and no work for the valve, and there is no change in elevation. That's the case. And so we come to two terms, velocity and enthalpy. The common assumption is that VI equals VE. And therefore, once the velocities are equal, then the enthalpies at inlet and exit are also equal. And therefore, the two equations that we usually use are 0 equals m dot I minus m dot E, and then you conclude that the inlet mass and the exit mass are equal, and the second equation is 0 equals HI minus HE, and with that we conclude that the inlet and exit enthalpies are the same. Now, let's see how this applies to a very, very simple problem, which is quite practical. The problem I defined it on the TV diagram, and the diagram is I draw a TV diagram. This is T, this is V, cubic meters per kilograms, and T as degrees C, and I draw the saturation line. This is the critical point where the properties are T equals 373.95 degrees C. P equals 22.064 kilopascals. And since we are drawing a TV diagram, I would write V equals 0.003106 cubic meters per kilograms. And this is our water properties. Now, we assume that we have a line here, which is 1,000 kilopascals. So on this line, P equals 1,000 kilopascals. And we assume that we have saturated liquid here. Okay, so the inlet condition I is saturated liquid at 1,000 kilopascals. And we have another constant pressure line, which is 100 kilopascals. And we assume that the exit is at 100 kilopascals, the inlet is at 1,000 kilopascals, and therefore a process happens which would look like this one. So E is here. And what we do now is try to find properties for this process and see what happens on such a process where a steam at 1,000 kilopascals goes through a throttling process and ends up at 100 kilopascals. So I would read the properties from the tables, and this is the table I'm looking at, where the 1,000 kilopascals line is here. This is the 1,000 kilopascals line. The saturated temperature is 179.88, and I just want to write the saturated liquid values. This is 0.01127, which is the specific volume for the saturated liquid. This is the specific energy, and the rest of them I just write them down for our problem. So what I have here are all the properties at point I. This is point I, where Pi is 1,000 kilopascals, Xi equals 0, which is saturated liquid, T sat for it, which is this point, is 179.88 degrees C, and other properties, Vf, which is this one, Vi, Vf equals 0.001127. You see, this is 001 and this is 003. So basically, this line should be a vertical line here, and we just draw it like this just for clarity and to make it distinguished. Otherwise, there's not much difference between points around this line. Now, the next step that I should take is with the exit condition. And as for the exit condition, what I shall do is to find the properties of saturated liquid and saturated vapor, and then try to see where the point E is. So if I refer to the tables and I move it to the 100 kilopascal line, which is here. This is the 100 kilopascal line. We could read the values of saturated temperature, VF, VG, and the rest of the data. We would, in this case, you would need both VF and VG, UF and UG, HF and HG, and we would need all properties for both F and G so that we could find values for E. This is what I shall write these things down on the paper. Well, these are the values for the properties at 100 kilopascals. These are steam properties, have nothing to do with our problem. These are steam properties anyway. And what I have found is that here, for example, the temperature is 99.61 degrees C, which is the saturation temperature at 100 kilopascals. Also, we have VF, which is 0.001043, slightly to the left of this one. This is 0.001043, slightly to the left of this one. And here we have Vg, which is 1.6941. This is 1.6941. This is Vg, and this is Vf. These are for the 100 kilopascal line. So what you have now is you see these two are properties, steam properties at this point, and this point. Now we have to add our problem to it, which is point I, which is here. Fair enough. Now we need point E. And what we have from point E is that HE equals HI. So as far as point E is concerned, we could write down that HE, with the assumptions that we just talked about, HE equals 762.51 kilojoules per kilogram. So the point E here has the enthalpy 762.51 kilojoules per kilogram, which is somewhere between 417 and 2,675 kilojoules per kilogram. So we can be sure that the final point E, is somewhere between saturated liquid and saturated vapor. So what we do is to calculate quality from this value. XE would be 762.51 minus 417.56 and divided by 2257.5, which is HFG for 100 kilopascals, and the outcome would be 0.1528. This is the quality. This is the quality, which is the ratio between the vapor mass, the mass of the vapor, to the total mass of water, whatever water we have. Now, with this knowledge, we are in a good position to calculate other properties of E. VE, a specific volume, would be 0.001043 plus 0.15 0.28 times 1.6941 minus 0.001043, and the result would be 0.2597 cubic meters per kilograms. That is uh, the value at E, which I should show it just here. It is here, and it is um, 0.2597. 0.2597. This is the specific volume, which is somewhere between the specific volume at saturated liquid and saturated vapor. This is the specific volume at the exit. We can also have other properties. We could have UE. We could, in the same manner, I won't just repeat it, but in the same manner, we could calculate UE, and the answer would be 736.48 kilojoules per kilograms. We won't need that, but still, we did calculate it for the properties, and SE is 2.2282 kilojoules per kilograms Kelvin. I shall later on, after I have finished with the first law, I will move to the second law and try to make some discussions there. There are very good points to learn from the second law of thermodynamics in this very problem. So we now have all properties at points 1 and 2. It would be very informative if we also draw the TH diagram for this figure. So since it is an H constant process, so what I would do is to draw a TH diagram, which this is T and this is H. And the TH diagram has a different shape. The saturation line has a different shape than this one. The shape of TH diagram is something in this way. In fact, in the TH diagram, the enthalpy of saturated vapor does not change very much for different pressures or temperatures. So what we do is we once again draw the constant pressure line or constant temperature line for the saturation condition, which is 179, 179.88, and for the 100 kilopascal line, which is 99.61. They are all in degrees C. And what we know is that this is their initial point, and this is the constant enthalpy line. So the value here, the enthalpy, is the same for both in exit and inlet conditions, and its value would be 762.51, and that compares with this value for 100 kilopascals. See, this is 100 kilopascal, this is 1000 kilopascal. These are the two lines, and the value for this point is Hg, which is 2675.9. 0. And basically, at the moment, we have all we need. This is point I, this is point E, and we have calculated all the properties for inlet and exit conditions. There's still a lot to learn from this problem, and I shall do that in the next video in part 2. Thanks for watching and cheers.